Okay, I think we can get started. Hello, everyone, and welcome to the Vision Seminar. It's a pleasure to have today Mengye to talk about continual and compositional learning. Mengye is a PhD student in the machine learning group at the University of Toronto, where he's supervised by Professor Richard Zemmel. And he also worked as a research scientist at Uber Advanced Technologies Group in Toronto, directed by Professor Eker Urtasun, where he does self-driving related research. He did his undergraduate in engineering science at the University of Toronto. And his interest is mostly in meta learning, fusion learning, and continual learning, where he has done a lot of very interesting contributions, from designing neural architectures to make training and inference more cost effective, using meta learning to reweight examples during training for more robust learning, and multiple works and benchmarks on fusion learning and meta learning. Mengye, it's a pleasure to have you here, and feel free to start.
All right, thank you for the great introduction. So I want to start with talking about a lot of successful computer vision applications these days. We're seeing a lot of machine learning based methods where we leverage machine learning to learn from the big data sets. And the standard approach we use today is to train on, say like for classification problem, we train using data sets that contain many classes. And the models are then expected to handle the classes in the training data, and it's often inflexible to add new knowledge at test time. And sort of beyond this classic IID machine learning, current research, we want to understand how to allow machine learning models to adapt at test time and potentially generalize to new distributions. And on the other hand, humans, we are very good at adapting a dynamically changing environment. And even if there are many new things and skills that we encounter every day, we're able to quickly learn them and store them in our knowledge base. So one of the holy grails of AI is to match human ability of learning in the natural environment. So the ability to adapt at test time really motivates us to visit the topic of few-shot learning. And the few-shot learning addressed the problem that standard learning algorithms require massive amounts of data. And by definition, few-shot means that we're able to learn a new model with only a few examples. So it has a mini training set called the support set and a mini test set called the query set. So typically for classification problems, few-shot learning has a fixed size episode to solve an n-way k-shot problem. Shots means the number of examples per class. So in the example here, we're learning new classes such as a cat, a sheep, and a pig in the support set, and to apply this knowledge to the query set. So here is another classic example where we're seeing an image of a Segway scooter shown in the red box, and we have it in the support set, and the task here is to learn the concept of Segway scooter and to classify which object in the query set is also a Segway. And you can imagine this setup can also be very useful for self-driving. With the growing popularity of use of scooters these days, we want to be able to recognize scooters without recollect another large data set with scooter annotations. So as I mentioned in the previous slide, one application of few-shot learning is in the classification setting. And more specifically, we often see this in the image domain. So we don't have to train like a huge model on 1,000 ImageNet classes, but instead we can just present a few images at test time and can able to predict them. So you can imagine this can also be applied in some other image domain, such that maybe we have a new disease, COVID-19, and we want to have a chest X-ray classifier that classify this disease. But we only have a few examples because the disease is still novel, and we are able to do this with few-shot learning. And aside from classification problems, it can also be used for regression problems. We can use it to forecast, say, the stock market tomorrow with a few observations in the past few days. And it can also predict the full image by only have a few samples at different locations. And lastly, few-shot learning can also be applied to reinforcement learning. So for example, the test time, the robot needs to learn a new skill based on field demonstration, or simply need to adjust to a new environment with different dynamics parameters. And for the purpose of this talk, I'm going to focus on the image classification settings. So we have defined what is few-shot learning. And in terms of the modeling side, few-shot learning is also very closely tied to the term of meta-learning. So here I will do a 1-minute survey on some of the few-shot learning methods. And I assume most of you are already familiar with them already. So the support set can be considered as a mini training set, and the query set can be thought of as a mini test set. And each episode are like a mini batch. So since each task have very few examples, we can actually imagine to roll out a small training and test procedure at each training step. And by treating each task as a mini batch, we can now meta-learn a learning algorithm. And what do I mean by that? Is that sort of learning a model prior or the right inductive bias for the task. So we've seen a lot of different ways of doing meta-learning in the past few years. So for example, in a protonet, they're learning better embedding such that the embedding is suitable to the average operation. So the average operation can also be thought of as a type of learning itself. In Mammal, learns the weight initialization, which can be used to quickly adapt to new tasks. And aside from weight initialization, you can also think of learning a weight attractor so that the weight will never go far away from the attractor. This is also the similar idea of learning a weight initialization. And we can also learn more basic things like, for example, example weighting, which is like learning a different learning rate for different examples. So there's also been attempt on the other end of the spectrum by fully parameterize a learning algorithm with an RNN. So these are a few examples of how we can do meta learning in practice. So the term of few-shot learning has gained a huge amount of popularity in the past few years, and it was probably first mentioned around 2015. However, recently there has been a lot of criticisms of few-shot learning, and probably the top reason is that the problem setup is simply not very natural, as in it is not how an AI agent is going to learn new object in the wild at deployment time. So let me be more specific here. First of all, few-shot learning has a fixed k-shot and n-way episode per class. So this means that we need to wait to collect n times k examples of a balanced set in order to start learning. So this is not how we wander in the natural world and encounter new examples. And every episode is a fresh start. So we don't combine with the previous n classes, nor do we combine with the next n classes. We throw away the knowledge every episode. There could also be unknown classes in reality that we don't deal with them. So currently the query set is just a closed set problem. So for few-shot to make sense, the query set probably should also contain out of episode distractors that don't belong to the class. And furthermore, there's only labeled examples in the support, but in reality, we encounter new objects that are not annotated. And lastly, there is a strict split between the support and query set. Now this might not seem like a problem in standard few-shot learning, but it becomes more problematic when we go into a continual regime where you can imagine a stream of input examples coming into the model. And now it's a problem to decide which examples in the input stream should we make it into a query set or the support set. So in theory, every example should both be a support and be a query. So fortunately, the research world has also proceeded very fast, and there has been a lot of papers that address one or a couple of the aspects in the list I make here. But none of them has delivered sort of the full package. So one thing that really motivates me is to ask, how can we design a more naturalistic few-shot learning paradigm and addresses all these natural aspects above? So this is one part of the criticism. And the other part of the criticism that I want to talk about is perhaps more concerning. So recently it has been found that regularly trained classifiers and without this support or query or meta learning at training time can get equal, if not better performance on few-shot learning at test time. So the way it works is that at training time, you just train a classifier just like the same way as if you train a regular CFAR or ImageNet classifier. And at test time, since you're going to see new classes we're going to throw away the classifier that's not useful anymore and use the embedding to train a new classifier, or just use nearest neighbor. And paper has shown that such a baseline approach can actually perform very well on feature learning. So this observation led us wonder whether we still need meta-learning techniques for feature classification or images or not, and what is the benefit of feature learning in general. So in this talk, I would like to talk about some recent works that attempt to address the two criticisms. So first is towards the fact that feature learning, at least standard feature learning, is not natural. So I want to introduce one of the recent work where we developed a naturalistic continual feature learning paradigm where we can accumulate new knowledge throughout time. It's not like we solve one episode and we throw it away and solve the next episode. And secondly, as I mentioned in the previous slide, that recent research showed regular image classification suffices for representation learning. But one thing that was missing in the classification objective is that it still lacks a compositional understanding of novel objects. It's more or less just driven by the local patterns of these images. And to address this, we develop a continuous embedding that is aware of the compositional structure. And more importantly, this is also an attempt to perform representation learning without class labels, and also with the current trend of unsupervised representation learning. So I'm going to start with the first part of the talk, which is about making continual feature learning paradigm. So I have briefly introduced earlier that we would like to model a natural agents that incrementally building up its own knowledge base. And one paradigm that has been studied a lot in the past is the incremental class learning paradigm. So for example, for CFA 100 datasets, it typically split up into 10 sequential tasks, where each of the tasks is a 10 class classification problem. And there is no review mechanism in this setup. So in the second phase of the training, you cannot see any of the classes that happens in the first phase of training. The evaluation is done at the end of each task learning phase. So as we see on the right image here, so this paradigm will produce 10 points, 10 evaluation points for learning these 100 classes. And this can also be too rigid because since the model needs to wait to collect data for 10 classes in order to start the next learning session. And before I introduce the paradigm that's going to be proposed by our work, I would like to share a view on the practical usage of continual feature learning. So I believe now we have been staying at home for almost half a year now. And one thing that I really wish to have in the future is to have a home cleaning robot for me. And in order to realize this dream, we need to let the robot recognize and use new objects. It will have an incremental knowledge system. So every time step, it will sometimes encounter something new, or it may enter into a new room or a new environment. And every now and then, it can also encounter an old object and go back into one of the old rooms and consolidate its memory. So not all frames are annotated because we cannot stay beside the robot and teach it all the time. So with this imagination in your mind, I'd like to introduce our paper, Wandering Within the World, Online Contextualized Feature Learning. And this is joint work with Michael Uzzolino, Michael Moser, and Richard Zemmel. So here is our proposed online contextualized feature learning setup. So this is an attempt to combine feature learning and incremental class learning. At test time, it aims to predict new and unknown classes in a sequence. So let's go over one example here. So maybe let's start with a world and an agent. And let's say the agent is wandering in the kitchen. So now agent encounters a cup. And since it has never seen a cup before, it will say it's new. And now we provide a label of the cup to the agent after its prediction. So now it needs to recognize clubs from now on. So the process we saw here is online and incremental, and the model also needs to predict unknown. There is no separation between support or query, since every example is also used for evaluation. And then we show a picture of a plate, and the agent also predicts it's new. So now we show the cup again. Now the agent makes a mistake here where it should have predicted class 1, but instead it predicts new. And lastly, we show the plate again, and the agent is able to say it's class 2. So note that the third and fourth example here are unlabeled with a dashed line, so the model doesn't receive the actual label after making the prediction. So it's also possible to have unlabeled examples to appear first, and before the world reveal its labels later. And this features the semi-supervised part of the learning paradigm. And model also predicts, the predictions are also evaluated after the sequence is finished. So now the sequence we see belongs to a scene in the kitchen, and these classes are correlated based on the context of the kitchen. And it can go on and on next to other rooms like the office and the living room. And now we can go back into one of the rooms we visited before to review some old objects. And within a room, the classes are correlated. It's also important to know that the context ID is not revealed to the model. So it needs to actively infer the context, and infer the context could be beneficial to the performance. So you can see the room or the context here kind of mimic the task idea in continual learning. So to further develop this learning paradigm, we start building some toy environments on top of the Omniglot dataset with handwritten characters. So here the images are presented in a sequence, and the top left corner shows the context, and the same set of characters co-occur within a context. So the red box here indicates the example is labeled, and gray dotted boxes are unlabeled. And sometimes the unlabeled examples can come earlier than labeled ones, and you can look at the first character, for example, where the label is revealed at the 4th time step. So we have shown that we can create such synthetic learning environment by making static images into sequences, but this is still not interesting enough, because what we are really interested about is online learning experience that happens in our everyday life. So the existing feature learning data set, however, such as Omniglot or Mini ImageNet, are based on static image only. So we have to manually design the online switching process and class distribution for generating this sequence. So instead, in this work, we consider directly use a more realistic learning environment. So here, we use the Matterport 3D environment developed by Chang et al., which contains 90 indoor worlds with panoramic imagery. And so we developed this data set by using those captures and call it the roaming rooms data set. And my co-author, Michael, has led this part of the project and spent a lot of time building the data set. So in this roaming room data set, the future learning concept is a little bit different than Mini ImageNet, because here we consider the task of instance-based future learning, where each novel instance forms its own class. So this could be a practical setting, because we can ask home robots to ask them to recognize new items. And in our experiments, we send the ground truth instance segmentation to the network, so it knows already which object we're referring to, and the network just needs to output the class, which instance, whether it's sofa number 1 or sofa number 2, for example. So the example sequence are shown in the video here. So now we have defined the task, and this lets us ask the question, what kind of model we can build to tackle the task? Is there any changes we need to make to adapt from standard future learning tasks? So here we show the online variant of a prototypical network for future learning. Suppose we have an online stream of object, we pass it through a CNN to get features, and we compared the features to the prototypes in the memory. So if it's outside of the radius of the closest prototype, it will be classified as a new object. And if it's inside, it will classify as the class of the prototype. And in order to update the prototype, we can use online averaging and just need to store another extra scalar C to denote the size of each cluster. So this could be a very simple model to build that directly adapt ProtoNet for this online setting. But there are still few things that hasn't been addressed. So first, since the objects are distributed according to the context, how do we model this temporal context instead of just passing individual frames through a CNN? And secondly, how do we determine the radius of each prototype, which predicts the new task, new class? And thirdly, how do we handle unlabeled examples? So with these questions, we introduce our proposed model, the contextual prototypical memory, to address the problems. And to model the temporal context, we simply add another RNN on top and add the features to the CNN feature to bias off the representation with the temporal context. And I'm gonna go into more detail in the next slides. And in addition, the RNN can also output the control parameters that including the radii of each prototype, which will decide how tight this concept is in your memory space. So I'm gonna talk a little bit about the implicit memory organization here and how does the RNN benefits the organizing the memory. So here is a conceptual diagram. So consider there are different prototypes scattered and being stored. So the color here indicates which environment these prototypes are from. And you might see an office chair in the office and an armchair in the living room. And because they are all similar types of objects, their mental prototype, just based on image features, might stay very close. But suppose that we add another temporal features to bias off the representation, this could potentially group closely, tightly together, depending on the latent environment, which is modeled by the RNN. So this shows how this could be possibly benefit the memory organization. So I want to also talk about how we plan to learn from unlabeled examples. So here we illustrate the reading and writing operation more into details. So when we read out from the prototype, we can use the radii output by the RNN, parameterized by the beta and gamma here. So the U hat denotes the probability of the unknown and whether the item belongs to a new or a known class. If the example is unlabeled and it also belongs to a known class, then we can actually update memory by using our own prediction. So, however, intuitively, the writing operation should be more conservative than the reading operation, since any mistake made here can actually have a very negative impact in the future. And therefore, we let the RNN to predict another set of beta and gamma in the writing operation, denoted by beta W and gamma W. So these are the different set of parameters from the reading operation. And we found that by using separate set of control parameters, this allows the model to have different conservative threshold for reading and writing, which is beneficial to a semi-supervised learning. And in our experiments, we compare the CPM model with a few competitive methods, including gradient-based methods, which is an online version of the MAML, and metric learning-based methods. We actually have won over already the online protonet earlier in the talk, and we also convert matching net and infinite mixture prototypes into their online versions as well. And lastly, we have RNN memory-based methods. So the DNC, which stands for differential neural computer, is an advanced version of a memory augmented neural network. So you can imagine they basically train the whole thing as a sequence-to-sequence task. So here are some results, and the metric here we're using is average precision, which measures both the known versus unknown prediction, as well as the accuracy for the known classes. And our model clearly outperforms other methods that we study here. And the gain is larger on semi-supervised setting, and showing that unlabeled examples can also be modeled as part of the temporal context by the RNN. And these are the roaming omniglot examples, and these are the roaming rooms results. So here is a video visualization of the model prediction as well as the roaming rooms task sequence. So we give the instance segmentation or the bounding box information in each frame, and then put the ROI features so that the model knows which object we focus on. And the moving of the camera and selection of bounding boxes currently are handled by the external environment. So model has no control over these things, but could be a very exciting future direction to go into when model actively choose which object to focus on. And on the top, we show the text label and model prediction. So correct predictions are shown in green and mistakes are shown in magenta. And on the right, we show a bank of instances that have been assigned labels so far. So again, in each time step, we send in the ground truth segmentation, and model needs to classify which class it belongs to, or simply say it's unknown. And as you can see, in this virtual environment, different viewpoints in the home actually makes up this implicit notion of a context. So before I end the first part, I want to make a quick connection of our modeling to the human brain. So the complementary learning system theory outlines different functionality of long-term statistical learning and the hippocampal memory system, where the hippocampus is basically for storing and recalling the novel concepts. So the hippocampus can also be further divided into working, episodic, and semantic memory. And here, the RNN in our model basically represents a working memory because it is transient and it stores the recent temporal context. And the prototype memory part consolidates multiple events into a single vector of concept, which is similar to a semantic memory. And lastly, the CNN part, although within a sequence, the CNN is frozen, but it's only updated in outer loop, sort of in the meta-learning outer loop. So it represents a long-term memory captured by statistical learning. So it learns to represent structure in the weights of the CNN instead of the activations, which is how the prototype memory stores stuff. So our long-term statistical learning is represented by this end-to-end meta-learning of sequences. So here, as a quick summary, we propose a paradigm for machine learning that emulates a human or an agent interacting within a physical world. So it combines multiple properties to create a challenging learning task. Every input must be classified or flagged as novel. Every input is also used for training. Semi-supervised learning can potentially improve the performance, and input and class distribution are conditional on the latent environment. So models we present here are meta-learned just like sequence-to-sequence models. So we propose two data sets for this paradigm, and in particular, the roaming rooms data set simulates an agent wandering within a physical world, and a new model called the contextual prototype memory. And there are a lot of open questions that are left to be answered in future work. So as I mentioned before, we can actually let the agent to actively choose which example to look at and query for label. So this is kind of an active learning extension of the project. And secondly, we can slowly adapt the CNN because currently the CNN is frozen in each sequence. And so this will limit its capacity when you see enough new examples in the new test domain. And lastly, it will be interesting to explore instance-based unsupervised learning because right now still everything is supervised. And we've seen a lot of success in unsupervised representation learning. And this could be a more natural extension of those unsupervised algorithms. So with that, maybe I can take some questions before I head into the next part of the talk. Okay, so maybe I will just keep talking. So the model we propose in the first part is still along the line of metric learning and feature matching among the training examples. In the next part of the talk, I want to provide another perspective of feature learning in terms of building a compositional understanding. And we want to be able to avoid the reliance of class labels during training, but instead using some other training objectives. So to start off, maybe it's worthwhile for us to review the original goal of feature learning that described in the paper of Brendan Lake and others in 2015. And the paper really motivates from a story of a compositional understanding. So as humans, the way we perceive a new object is like the Segway scooter by decomposing it into smaller parts. So for example, the handlebar, the body, and the two wheels. And the same intuition also applies to novel characters. But in deep learning, we make use of massively labeled data set and data augmentation to make feature matching very hard to beat. So maybe we should take a step back and think about the compositional aspect instead of just relying on learning feature representation. So in that paper, it also illustrates a way of building an inference engine for strokes of handwritten characters. So the idea is that if we are able to spatially decompose a character with strokes, then we can use it to classify characters. So they propose a hierarchical Bayesian model that aims to perform analysis by synthesis. It starts with a bunch of stroke primitives, and then it composes parts and subparts, and the relation groups the parts together and represents the program. It has nice properties of compositionality. So however, even for strokes, the inference procedure is basically involves inverting the entire probabilistic model, can be very cumbersome. And also it's unclear how to scale this model up and infer the structure of natural images. So beyond the handwritten characters, when we process natural images in our head, the sketch strokes are also very intuitive representation of the complex visual scene we see, and preserves the most of the salient features of the original image and serves as a mental prototype. So here are some examples of the kangaroo here and the $1 bill. So it looks nothing in detail similar to the original image, but we get the idea. So the BPL model I showed in the previous slide is essentially a hierarchical deep generative model where the generative process P of X given Z is well defined, but the posterior distribution P of Z given X requires a prolonged inference procedure. And we've seen the success in variational autoencoders. The inverse can be replaced by a feed-forward neural network approximated by Q of Z given X, because neural networks are powerful and efficient inference machines. So now if we apply the same intuition here, so where BPL is a generative model that infers the stroke and motor programs in the latent space and generate image pixels. So instead of performing exact inference, can we also replace the inference process with a neural network that takes in a pixel image and output a motor program? So in fact, this direction has been explored almost 15 years ago in a paper by Hinton and Nair in 2006, where they tried to learn a network that can output a motor program that draw each MNIST digit. So for each digit, there is a separate network being trained, and it estimates the XY shift of coordinates from prototype drawing. And by the motor program, it's really just a fixed dimensional vector representing the location and shift from each point. So Hinton and their 2006 paper shows that it's indeed possible to use a neural network to perform inference from pixel input and output the motor program of stroke drawing. And this shows that the recognition network has a lot of capacity. But we can see that output space is rather naively designed because this one is a fixed dimensional vector. And later on, we've seen that the output decoder can also be upgraded. So this is shown in Alex Graves' 2013 paper. We're using an LSTM to generate the handwriting sequences using a sequence-to-sequence formulation. Another creative design of the paper is the mixture density output. So representing each stroke with the mean variance, covariance, and the mixture weight parameter in the output of the hidden state of the LSTM. So this allows us to sample different modalities of the drawing. So the drawing is not deterministic. And this kind of model is further being upgraded later in 2018 in the work of SketchRNN by Ha and Ek. So now it can be applied to general sketch drawings and not just handwriting. And both of these work I've shown here didn't use a CNN as encoder, but they just encode the sequence and try to decode the sequence. So it's not really about image understanding. And on the right, they also show an embedding space that can learn some form of interpolation in the sketch space. And after I introducing these background work, and inspired by these advances in sketch inference and autoregressive generative modeling, I'd like to introduce our recent paper that tries to perform sketch inference on generic images by imitating human drawing. And the first author here is Alex Wan, who contributed tremendously to this project, and this is part of his 4th-year undergrad thesis. So if we represent the compositional structure of images using discrete strokes or discrete programs, this representation can be very hard to deal with, especially when we compare whether one program is similar to another program. And ideally, we like to have a continuous image embedding that has some compositional understanding. And this motivates us to build an encoder-decoder model. So let me be clear what I mean by this. So let's start with that image pixel X, and then the encoder model maps the image pixel to a later representation Z, and decoder model maps the representation into pen strokes, and later we can use a renderer to map it back to the image space. So we refer this intermediate representation Z as the sketch embedding. So the intermediate representation has the benefit of a continuous representation while it is still driven by the sequential generative process. It can be hopefully capture some compositional features. So more concretely, this is a look of an image, and the encoder, we use a CNN to map into Z, and then decoder, we simply use a sketch RNN. So that was kind of the model. It was really straightforward. We just want to see how we can push the limit of this kind of encoder-decoder model. And then we found that the most success ingredients lies in the data. So one of the data set we use is this quick draw data set, which contains a lot of human sketches and drawings. So there are 345 object classes, and in total, there are 50 million drawings. So this is a huge data set, and hopefully we can leverage the information from this data set to build some general image-based understanding. And in the natural image space, there is the sketchy data set, which is much smaller than the quick draw data set, but still quite enough data for us to work with. And there are 125 classes, and in total 100 photos per class, but there are multiple sketches per photo. So in this setting, if we do it on natural image, this is going to be a supervised setting because the input image is sourced from ImageNet as supervision of human drawn sketches, whereas the previous setting is basically an unsupervised setting because the input is basically the output. We're looking at the sketch and we're trying to reproduce the sketch. So here I will introduce the training objective of the model. So it's a combination of the pen loss, which classifies the 3 different pen states, whether it's down or lifted or terminated, and the stroke loss, which maximizes the likelihood of the ground truth stroke. And lastly, there is a pixel loss, which tries to match the generated drawing with the input pixel image. So this is achieved by the differentiable rasterization function, and we can apply some blurring operations so that the pixels only needs to be loosely matched. And the training is done by teacher force. So also I want to emphasize that in this paper, we really try to push the limit to draw all kinds of classes. And the previous thing in SketchRNN or some other previous work, they only try to draw 1 or at most few classes per network. So for example, there's also been work that's done on the shoe and chair sketch data. And there's a body of work that produce visually appealing high quality sketch, but goal is not to learn a general embedding function. And since our goal is to learn a general embedding function and capture the composition of novel object, we will let the same shared network to draw hundreds of classes in the data set and essentially train a generalist sketcher. And since we are also using the sketchy data set, so we are also the first to attempt to draw a general sketching model from an open domain of these natural images. Although I have to admit that you'll see later in the slides, the quality of the sketch on natural images is not that impressive. So here are some sketch results. And on the left, you see in the boxes the image that we provide to the model, and on the right is the model outputs. So you can see these are the seen classes during training, but these are the unseen images. And here are some failure cases. They still captures the basic shape, but I would say the alignment of these points are sometimes not perfect. And here are some unseen classes. That means the model hasn't seen any basketball during training, but simply presented this image and then asked to reproduce the image. And here are some failure cases as well. And these are the natural image domain. Still some interesting successful cases here, especially for the jellyfishes and the sailing boat. And for the unseen classes, sort of also recognize the circular shape of the pastries and the shape of the pottery and perhaps the boxy composition of the storefront. I also want to show a little bit on the embedding space visualization. So here we show a few different images varying their angle and distance, and we try to project into the embedding space to see what it's doing. And on the VAE model, we see like a clear clustering effect of this input image because they basically differ in the pixel. And more interestingly, we can see a linear continuum that defines the angle and distance in the embedding space of our model. So perhaps this is not surprising since the model is trained to use motor control to produce these images. So it does need to have an understanding how far it should move to draw the next circle. But keep in mind, both are using the same CNN architecture to produce these embeddings. And next, we can project different kind of spatial composition. And the VAE model kind of confuses these concepts, especially hard for this one where we have 2 circles and 2 squares that are located at different positions, whereas our model can clearly cluster these into different classes. So there's also this notion of conceptual composition. Basically, if we recall in the NLP literature, there's king plus woman minus a man equals queen. And in the generative adversarial network literature, we have also seen papers that attempt to perform latent space operation by adding, say, like a pair of sunglasses. So inspired by this, we do the following experiment where we start with a snowman, which have 2 or 3 circles, and we project this image in the latent space, and we minus embedding of a circle and add an embedding of a square. And what we get is a stacked squares, which is very interesting here. And we can also do the same thing. We start with a TV, we minus the square, add a circle, and we get a donut here. But on the other hand, the VAE cannot do such operations as expected. So now I want to come back to the topic of the talk is based on visual learning. So we also try to see how this embedding can facilitate visual learning of novel concepts. So the procedure is very simple. We train the sketcher and then just use it at evaluation time for visual learning benchmarks. We use the sketch embedding and extract the features and learn a linear classifier on top of these features for novel concepts. And we compare our models to other unsupervised visual learning model because unsupervised means that there's no class label given during meta training time. And in fact, for Omniglot, we didn't need any other additional supervision. For ImageNet-based visual learning, we did need human demonstrations. And these are some competitive methods. Cactus is based on the clustering of different data points, and another 2 AAL and Amstra, and it's based on data augmentation of input images. And we also compare to another 2 baselines, the random CNN, which having just random weights, and a calm VAE model for basic representation learning. So there are 2 model variants. So ours is basically trained on the Omniglot data only because Omniglot also contains human sketch sequences. And ours S is directly trained on quick draw data because it has a much larger number of examples and transfer directly to the Omniglot visual learning tasks. So let's see what the result is. So here, the best performing model is our set, which is only seen on quick draw data. This is tested on 20-way and one-shot and 20-way five-shot episodes, and it gets the state-of-the-art performance comparing to all the other unsupervised few-shot learning models. And so this demonstrates that embedding can actually generalize. And just as a reference point, here are the supervised models such as MAML and ProtoNet. So our model can beat MAML and closely matching the supervised numbers with the ProtoNet on OmniGov. So this is very exciting numbers. So here, I also want to show some ImageNet numbers because we have trained on the sketchy data set. And so this, we will call it weakly supervised because it does use human sketch as supervision, but not using class labels. And here still, we are able to outperform other numbers. I admit that this is not like apple-to-apple comparison, but just as a reference point, it can also perform few-shot classification. And these are the reference points of what a supervised model would do. So it still has a little bit gap towards the supervised counterparts, but I feel like this is very promising progress. So there are, of course, a ton of things that we wish to work on in the future on this work. So first, we need more systematic evaluation of compositionality that's beyond simply visualizing the embeddings. And few-shot classification, on the other hand, can give us a concrete number, but we are not sure what kind of compositionality the model is generalizing to. And another interesting direction will be removing the reliance on the imitation loss. So as purely driven by the pixel loss. So this seems conceptually easy, but we haven't figured out the right way to train the model yet. And we have seen a more expressive decoder can really make a difference here. So progressing from Hinton and their 2006 paper where we only used 17-dimensional vector and towards the sketchy RNN, which is more capable model. So maybe it's time to upgrade the RNN decoder again so it can produce general drawing. And so when will we be able to produce a full painting with more expressive decoder? And there's also a very exciting work recently called Deep SVG, where they propose to generate SVG graphics with Bezier curves and other primitives. So this all seems to be very exciting, one level up to make the decoder more expressive, since we have only looked at generate piecewise linear strokes. And lastly, I would like to give a summary of today's talk and discuss what's next for few-shot learning. So a few years ago, few-shot learning was designed to see how well we do the features learned on a set of training classes and how well we can generalize to a novel test classes. And there has been a lot of success stories. So we used to criticize that supervised deep learning don't generalize to new things, but we later found out this is not entirely true. At least for image classification, the pre-trained features generalize pretty well for classifying new items. And this is probably not super interesting to test ImageNet-based few-shot learning benchmarks anymore. But it's still an interesting test bed for unsupervised representation learning to see whether or not the learner representation can discover new concepts at test time. So on the OmniGlaw dataset, for example, where the supervised few-shot learning has absolutely already solved the task, we show that we can still improve quite a lot on the unsupervised benchmark by using a different training objective. And more interestingly, our best performing model was not only unsupervised, but also trained from a different domain, just based on a very large number of drawings. And in the future, it will also be interesting to look at more structured tasks, such as question answering or IQ questions, for example, just beyond the few-shot learning of classification of images. And in the first part of the talk, I covered the concept of continual few-shot learning, and there will be a paradigm towards more natural incremental learning process, which is one of the original motivation of developing few-shot learning. So it performs fast retrieval of the recently learned novel concepts. And here it seems like meta-learning is still relevant, since we should be able to meta-learn the fast retrieval algorithm on top of the learned feature in a dynamic environment, and also deal with the challenging open set recognition problem. So lastly, I'd like to end with an open question. So would there be a continuum between few-shot learning and regular learning? So in the recent past, all the concepts are being stored on the few-shot level. And once we've seen instances for many more times, we can further fine-tune the representation of the lower layers. So we don't necessarily need a separation between few-shot learning and regular learning. So it can all be trained in a sequence. So we can start the representation learning process when we press the power on button of a robot, and the robot doesn't have to be pre-trained with other prior knowledge. So that will be the end of my talk. And lastly, I would like to thank again to my collaborators and my advisor. And these two projects would not come to reality without major contribution from them. And thank you all for listening. I will happy to take your questions.
Thanks a lot, Mengye. That was great. We have time for like 2 or 3 questions. Feel free to unmute them. So somebody wrote in the chat.
Maybe how do
I can read. I can read it for you if you want. So Vikash Kumar is asking how RNN help to derive the radius using context parameter is not clear to me. Can you please give some intuitive explanation?
Yeah. So maybe I can show a additional visualization on the control parameters. Just let me look for the slide. Sorry, the control is a little bit. Here. So, so basically, by looking at the past history, the RNN is supposed to give the control parameter value. So this could be a condition on what you have seen in the past, or can be conditioned on the current progress into the sequence. So this here we visualize how beta and gamma evolve over time. And here are different curves on the reading and writing parameters. So you can see that here, the beta R is greater than beta W. So this indicating the writing is generally more conservative than reading overall. And the gamma W grows over time, right? So this indicates that the slope is less sharp over time, and the writing becomes less conservative over time because we have already accumulated certain knowledge in each cluster. I don't know if that answers the question.
So as a follow-up to this, I'm not sure I understood, like when you're doing inference, you're just doing like a sigmoid. Does this mean that each instance is not like mutually exclusive with the other classes? Like,
so basically at the inference, we're trying to give a value on how likely this object is a new class or an old class. So this is a binary kind of prediction, whether this is new or not new. And then there is also a softmax classification that's saying which class it belongs to. So we can choose to how we want to decode this. So say that we can say set the threshold at 0.5, and then we say if this guy is this guy is above 0.5, then we're going to say it's new. Otherwise, we're going to say it's one of the softmax.
Thank you. Are there any other questions? Okay, then I guess we can end it here.
All right.
Thanks so much, Mengye. This was very interesting.
Thank you so much. Thank you so much for having me here.